Good afternoon, everyone. We are Group 3, and our project aims to aid the reaching function for ALS patients through an assistive passive exoskeleton. As we've learned in class, ALS is a degenerative disease causing motor neuron loss, leading to loss of muscle control. In terms of the arm function, it begins with loss in finer motor skills like writing and progresses to difficulty for patients moving their upper arms and reaching to eat. We are focusing on patients at this stage of ALS, and for good reason. After research and interviewing an ALS caretaker, we found this stage to be a turning point for patient independence and morale, where the inability of a patient to feed themselves leads for being one of the most demoralizing stages of ALS. Furthermore, physical activity is the most effective method to slow ALS progression due to increased neurotrophic factors, thus slowing motor neuron loss. This thus motivates a patient-driven assistive device. Now we'll go on to our solution approach.
In developing a solution, we began by creating a kinematic model of the arm, with a 3 degree of freedom ball and socket joint at the shoulder and a revolute joint at the elbow. The corresponding DH table is shown below the schematic. With this model, we derived the dynamics of the system using the Lagrangian method. The simulation on the right shows the system moving under the influence of gravity. We validated the dynamic equations by showing conservation of total system energy. In the plot, kinetic energy is shown in red, potential energy in blue, and the total energy, which is constant throughout the simulation, in black. The dynamic equations allowed us to appropriately gravity balance the arm, which we will discuss next. In designing our exoskeleton, we found that we could simplify the dynamics of the human arm by shifting the forearm's center of mass to the elbow. Statically, the arm becomes equivalent to a single link representing the arm, connected to a ball and socket joint for the shoulder. The equations for gravitational potential energy of this simple system are shown here. In order to shift the center of mass to the desired position, our exoskeleton adds a counterweight behind the forearm. Standard values for the forearm length, mass of the forearm and hand segments as a percentage of total body mass, and the position of the forearm center of mass relative to anatomical landmarks were retrieved from anthropometric tables. The bottom left equation relates the counterweight mass and distance from the elbow to the subject-specific anthropometrics. We found that a lighter 0.8 kilogram mass and a heavier 1.2 kilogram mass at distances of 6 to 12 inches from the elbow would be effective for a wide range of subjects.
With this analysis in mind, we designed an arm orthosis that contains a suitable forearm counterweight that allows us to leverage the simplified dynamics we introduced before. We then added a gravity balancing system to our exoskeleton, accomplished through a spring that is attached from a point directly above the patient's shoulder to a point on the upper arm portion of the exoskeleton. The spring has a potential energy shown in the figure to the right. Adding this to the gravitational potential energy obtained before, we see that the potential energy can become configuration independent. That is, it becomes constant in all positions, if the first term is cancelled. This is achieved in our design by matching the spring stiffness to the quantity shown below. Furthermore, we can also play with the position of the spring to further tune the gravity balancing of the device.
The CAD rendering of the device was designed to illustrate its real-life applications. The exoskeleton and gravity balancing design assist the user in maintaining a maximum use of their arm. As it is intended to be mounted on a wheelchair, the patient does not bear the weight of the exoskeleton, and it can allow the user to reach and grab with their right hand and maybe control the wheelchair with their left. The spring is seamlessly routed to the back of the wheelchair as to not interfere with the patient, and it also allows the spring to fully compress and extend. As shown in the simulations below, this design enables enhanced arm mobility with a minimal load through the help of a weight-bearing spring. A patient is able to reach out for food and feed themselves, allowing them to retain independence and exercise their muscles. Since the patient can now feed themselves, this also reduces their dependency on a caretaker, even for a multitude of tasks such as brushing their teeth, cleaning their desk, and reaching for items such as a remote.
In conclusion, we created a design for a wheelchair-mounted assistive exoskeleton that helps both the patient and the caretaker. Through our kinematic and dynamic analysis in MATLAB and by creating a working CAD prototype with readily available parts from McMaster, we have shown the gravity balancing functionality of our device and its feasibility. Passive assistive devices can offer a lot of assistance performing activities of daily living without the need for batteries and motors, and further work could expand on this potential. For our next steps, we would like to create a scaled physical prototype so we can test and calibrate our design for maximizing range of motion and usability. We would also like to expand on this project by integrating some form of grasping assistance, and also explore using actuators in the exoskeleton for more impaired patients. Thank you for listening. We will now go on to Q&A.